Hi, in the last video we have discussed about the basics of KNN and also some failure cases for the KNN. Basically, it is not good to apply the KNN when that failure cases we have data like that. And the main thing in this video we are going to discuss about the K. What is the basically K represent the number of neighboring points we have to consider during the training and the testing. And basically the K is a hyperparameter. Let me now tell something a difference between the hyperparameter and parameters. The parameters are get by the training on the data, and but a hyperparameter is it our hands. And by changing the hyperparameter values we are going to get the some performance also, and we can increase the performance. I'm telling. And a few libraries, and then basically all libraries having their default values for the hyperparameters, but also we can change that. Also we will see when we are using the sklearn library also. Now let's deep dive into the some things like what will be happen when we consider the k value is low, when we consider the k value is high. Those things we will discuss in this video basically. Let us consider this as a toy dataset. The red points represent the positive points, and the yellow dots represent the negative dataset we have. And the same for this one also. Now, our main thing in here, we have to know what will happen when we are changing the k value. Let's consider now for the let's consider k is very low value. The k low value is 1. When consider k value is equal to 1, in this way we have to look every point. By this way we will get the plane. It's not a smooth plane we will get, because we have to look at the every point in the data. By this way we will get the plane like this. This is not a smooth plane. It is untrained data. Okay, this data is a trained data, let's assume as of now, and the errors are 0 here when we consider k value. And let's see when we have the some higher value, let's consider k equal to 5. When we consider k equal to 5, at that time we will get the plane like this on the trained data. Yeah. It is a smooth curve because there is no like that here. Yeah. It's a smooth plane. But here we can see some errors also is there. This is classified as a positive class, even though it is a negative. And similarly this red class is classified as a negative class, even though those are positive classes. And errors are there. Errors equal to 4 here. Errors are there 4. Now let's say take a query point, then how this is going to work. Let's see that thing to get more understanding. Let's consider a query point in this region. It is good to use another color, I think. Let's go with blue color. Let's say consider a query point q, xq is here, and when we consider k value is 1, it only look at the nearest neighbor 1 point, the closest point to the query point. Here it is this point is going to be the nearest point. This point going to be nearest point, and the query point is classified as a positive point. By the clearly looking we can tell this is a positive point. Sorry, this is a negative point. The query point is a negative point. Let's see. If we just move this point, if we slightly change the query point now, I will use different color. If you slightly change the query point, now the nearest point is going to be this one. And this point is going to be negative. And the query point is classified as now negative class. By changing the just a query point slightly, the entire class going to be changed. This is a big issue. This big issue we are going to tell is a overfitting problem. This is a overfitting problem. When k equal to 1, we have the overfitting problem. Here see, let's see here. There is a xq. x1 is k. This point is k. It will be just look at the nearest 5 points. Let's consider these are the 5 closest point to this data. Let's consider like that. Not this one. This has to be considered. That's fine. But generally we are going to use a majority based approach. Here the negative points are 4 and positive value is 1. Majority is negative classes are there, then we classify as a negative class. XU we classify as a negative class. And similarly, if we consider a query point here also, under this also find the nearest 5 points. Here also we have 4 positive points, 1 is negative point. Majority is the positive class, then XU classify as a positive class. By this way, by taking some reasonable k value, we are getting the better results. That means we have very less problem here. This is a normal condition. Let's consider the higher k value. What will be happen? If we consider higher k value, let's consider k is going to be number of points in the data. Okay, let's suppose in the data we have 20 data points. Let's consider 30 here. And here 20 belongs to positive points and 10 belongs to negative points. This is considered like that. Even you give a query point xq, a query point xq, at that time it look at all the points in the data and use the majority technique. The majority is positive points only. That means if we give in every query point, it will give as in positive. Is it anywhere? If it is here or here or here, anywhere it is, it's only give the positive points, positive class, because the majority number of majority points is going to be more for the positive class. That's why it was giving the positive class. This is also a big issue. This we will call as underfitting problem. Now we have basically two problems are there. When the k equal to low value, we have overfitting problem. And when we consider k equal to very high, now we are going to get underfit problem. How we can get the best k value? To find the best k value, we are going to use the k-fold cross-validation technique. K-fold. Here is the k is the number of folds. K is the number of folds we will make the data. And this k is not the same as k in KNN. A lot of people has some confusion about this k values. This k is different from this k in the KNN. This k is the number of points number of neighboring points we have to consider. This is the splitting the data into folds. How many folds we have to split. Let's see how we achieve the best k value by using the k-fold cross validation technique. Basically, we have all data. We will split the data into train and test. We will train our model on the train data, and we will check how the model performance by using the test data. We will try different models on the train data and check the performance on the test data. The which giving the best performance, we will go with that model. That was general approach in the finding the best model. Okay, but here to find the k value, we are not going to, it is not good to use the test data directly to find the best k value. Instead of that, we will split the train data into two parts. We will split the data into D train and D cross validation, and as normal we will use the test data for the testing the model. For the finding the best k value, we are going to split the train data into train and cross validation. In the k-fold cross validation, let's consider k equal to 4. That means we are going to split the train data into 4 folds, and generally the k values lies between 4 to 10. It's fine. Let us consider this is a D train data. Now by using k-fold cross validation, let's k take as 4. We'll split the data into 4 folds. Let's consider the first part as D1, D2, D3, D4. Now let's see how we are going to use this data to find the best k value. To find the best k value, we have to consider some k values. Let's consider k equal to 1, 2, 3, 4 to 10. Let's find. We will find the best k value between in this list. First start with k equal to 1. We have data is in k-fold cross validated. D1, D2, D3, D4. Now when k equal to 1, we will consider D train, D cross validation, and for the performance let's use accuracy. For the D train, we are going to use D1, D2, D3. We'll combine these all the data set. We will form one single data, and we will use that as a training data with k equal to 1, and we will test this trained model on the cross validation data. Okay, that we are going to use D4, and we will get some accuracy A1. Let's consider. Similarly, when k equal to 1, and here we are going to consider data is D2, D3, D4, and the cross validation data we are now consider as D1, and here we will get accuracy. Let's consider A2. Similarly, k equal to 1. Now the train data is going to be D3, D4, D1, and the cross validation D2, and accuracy A3. Similarly, k equal to 1. Now the train data is D4, D1, D2. Now D3 is going to be cross validation data. A4 is the accuracy. By this way, we will test the our model on all the data set. Here we can see we tested on D4, D1, D2, D3. Okay, now we got the accuracies. Now we'll take the average A1, A2, A3, A4. Let's consider this one A1 dash. And similarly, now k equal to 2. For the k equal to 2, D1, D2, D3 as a training data and D4 as a cross validation data, we will get some accuracy A1. K equal to 2, then data will be D2, D3, D4, and D1 is the cross validation data. A2 is the accuracy that we will get on the D1 with k equal to 2. Similarly, we will get up to A4. Now we'll take average. Here we will get A2 dash. Let's consider. For the 10 k values, for the 10 different k values, we are going to apply at every stage. Now, for the 10 k values, okay, k values 1, 2 up to 10 we have. For this all 10 k values, we will get some accuracy from the model. A1, A2 dash, A3 dash, A4 dash, like that, A10 dash. Now we will check the best accuracy. That means that giving the more accuracy in this with this k value. With which k value we are going to get the best k value. Let us suppose the AF5 dash is more. That means we are going to consider k equal to 5. Now let us see how it's going to be, the error is going to be changed when we change in the k value. For that we are going to plot or something. Let's see that one. Yeah, here we can see the x coordination is k value. That means the number of neighbor values we will consider, and the error that we will get. For the test data, when we consider the lower value, we have more accuracy we will get on the train data, but we will get the less accuracy on the test data. That means more error will be happen on the test data. That means when the k value is low, the error is more, and as the k value is going to be reduced, then error also going to be reduced, and after some time the k value is increases, the error also will be increases. This is on for test data. Let's see how it's going to be on the train data. Generally the error will be very less when we consider the lower value of k. As the k is going to be increases, error also going to be increases on the train data. This is for the train data. The best k value is this is the point. This is the best k value. Any value, let's consider k equal to 7 is the best k value here. And one more thing here is, when we consider the lower value of the k, it's going to be overfit problem. This is the overfit area. We don't need the k value in this range. When we consider higher value of k, we are going to get the underfit problem. We also don't need the k value in this range. Okay. Now we only need the k value in this range only, and the best k value is this k value that we have to consider. This is the overfit problem. This is the underfit problem. This is a good k value, and once we will get the best k value is equal to 7, let's suppose here, and we will test on the test data.